I'm Andrea, your host for today's webinar. I'm glad to welcome Eve, who will present security requirements for connected MCUs and MPUs, modeling of a SESIP profile. Eve is an expert in security evaluation and certification of IoT products at NXP Semiconductors, chairman of the SESIP task force at Global Platform, and has more than 10 years of experience in IT security evaluation labs. During today's webinar, Eve will briefly introduce the SESIP profile methodology. Then we will discuss on the core MCUs and MPUs of SESIP profile. And later on, she will explain how these enable an efficient security assessment and how they support compliance demonstration of several devices towards several IoT standards. Before we start the webinar, I would like to do a little housekeeping before we get started. As usually, today's webinar will take 30 minutes, followed by a 10-minute Q&A. If you have any questions, I would like to ask you to send them across the Zoom chat box, and we will read them out loud after the presentation is over, and we will answer them. And we will also record this webinar and upload it later on our YouTube channel. Without further hesitation, I would like to invite you, Eve, to start your presentation.
Thank you very much. Oop. So I will share. Okay. So thank you very much for my presentation. I will now show how the core what we call the core MCU MPU SESIP profile can help raising up the security in the IoT ecosystem. So for that, briefly, we will start with an introduction on MCUs, MPUs in IoT devices, then see the main principles of and contents of the core MCU, MPU SESIP profile, and finally have a focus on how the security assessment and in particular in the testing is done following this profile. So IoT devices are devices interacting with their direct environment and with other remote devices through a network connectivity. Those interactions with local and remote environments are allowed by central units based on microcontrollers, or MCUs, or microprocessor, MPUs. And of course, those ones are exposed to attacks. As those IoT devices are already everywhere and as their number are continuously growing, the security need is of course also rising, and more standards and regulations are popping up, trying to put security in those IoT ecosystems by defining security requirements to be implemented by the IoT devices. And those standards are coming from everywhere: US, Europe, Asia. Examples being the EN 303645, IEC 62443, the NIST 8259, but there are way more, as you can see on the image. Now, the problem is that those security requirements are for the final devices, but those MCU, MPUs unit parts of IoT devices are quite complex. They integrate many different subcomponents that can be hardware, software IPs, modules, and which can be coming from different developers, which makes a security analysis at the final device level almost impossible or unsustainable in terms of effort and cost for the IoT vendors. The OEM or final developer, the one who is at the end of the productions, let's call it IoT vendors to simplify. And so this IoT vendor will definitely need the support of all the subcomponents providers to be able to gather the security information for the final security assessment and demonstration of compliance with the IoT standards I just mentioned before. And even gathering all the information from all providers, this is not enough to make security assessment about the integration of those components with each other. So in summary, it will be too much effort and maybe not even feasible for IoT vendors to handle a security assessment of a full IoT device from zero. So even just showing the compliance demonstration of the final device to the security requirements of the IoT standards and regulation will be way too heavy. And so if it's heavy, the IoT vendor will just not do the security assessment if not mandatory. They will lobby against this becoming mandatory, of course, and we will continue with so many untested products in the field. Also, from a manufacturer point of view, his product could be integrated in many different devices. So it is also needed that effort to provide evidences by the manufacturer for IoT device levels can be reused and are not repeated for each IoT device case. So this is why it has been seen needed to have security assessments at subcomponents level and to have the possibility also then to assess the composition between subcomponents, as it can induce specific security concerns that should be checked and potentially tested. And this is what the SESIP evaluation methodology has been developed for. The idea is to be able to build step by step a complete security analysis of what is called the IoT platform, which is in green here, and which is in fact the part of the IoT device implementing the main security features invocable by the final applications, final IoT applications. And that was a very important focus on the reusability of evaluation results. The reuse is for composition with other subcomponents, or reuse as evidences directly for demonstration of compliance to security requirements from those IoT standards that we have mentioned. So the first step for building this security assurance of IoT devices is to evaluate the security of the core MCU MPU, meaning the MCU as it will be provided by the initial hardware developer, manufacturer. And for this, in SESIP, a specific security profile has been developed. So first, very briefly, SESIP profile is simply a document in which will be defined the minimum security claim to be done for same type of product. Concretely, you will find in a profile the description of the product type, the physical and logical scope of the security evaluation, the use cases to be considered. We will see why it is important for security testing, for instance, the minimum security features to be implemented by the product itself, and the potential conditions and to be fulfilled by the environment to ensure the security of the product. That being said, the MCU MPU SESIP profile in particular identifies those core security features to be implemented as the root of security for the full final IoT platform. So this list of core security features are not coming from nowhere, of course. They have been determined by several MPU and MCU manufacturers, their customers, taking into consideration their own product and the security requirements that were common, that has been found to be common to the main IoT standards, again, that we have mentioned previously. So those core security features are summarized here. The first one, the secure identification, is a base requirement in security assessment in general to ensure that the customer cannot be fooled about the product he's buying and has in his hands. The secure initialization then, which is basically the secure boot, is of course fundamental to ensure that the firmware running is the expected one, is in its expected version and has not been modified. The secure update that can be part of the secure initialization process also is again an essential mechanism to allow update of the firmware. This is in particular important when used to fix bugs or even security issues. Then you have the residual information purging. This one is to provide the final device with the capacity to ensure that no user data will remain in memory. It will typically be needed in case the decommissioning of the device or if needed to be sent back to the manufacturer, for instance, for investigation. Or for factory reset before reconditioning or for resale. Secure debugging is also a very sensitive feature that need to be claimed and evaluated in case it is a service provided by the MCU. So all those features are the mandatory features that had been identified as common to the IoT requirements. The following ones are optional for their own different reasons. So the cryptographic features may not be part of an IoT device, depending on the intended usage. For instance, you have devices with low resources that are not directly connected to the wide network, but to a local one with central units in charge of the heavy operations and then the connection to the wider network. So this is an example where the cryptographic features are not mandatory, and this is why it's optional. Optional also, some of the assets and operations may need to be handled in a separated execution environment that we call secure enclave, as for instance, the storage of the private keys and or the execution of cryptographic operations. So the secure enclaves need to be an enclave, of course, meaning with its own separated execution means, but inside the MCU and secured in some way by software or hardware means. So it can provide a higher level of security or not, but it must at minimum be providing either a logical isolation or hardware protections. Which bring us to the last type of security features, the ones from a category called extra attacker protections. So these are related to the environmental conditions under which the IoT device is executing. Basically, by default, in SESIP, the IoT device is expected to be manipulated by trusted users only, and only containing trusted code that cannot attack it or be used to attack the MCU MPU. But if untrusted users or untrusted code are considered, and protection then are implemented, this is possible to claim those additional protections to demonstrate that the MCU MPU can be used under those more hostile conditions. We will come back more in details on these use cases when we will discuss the security testing parts. So in the core MCU MPU profile, those core security features are organized as represented here. So mandatory features are defining what is called the base profile, and other features are in form of optional packages. And those core security features are implemented, as said before, by the initial hardware manufacturer. So this is what is expected. And it's expected to be implemented as represented here on the right. Then in the lowest part of the IoT devices, the hardware and the corresponding firmware. So the profiles identify both the security feature to be implemented and evaluated, and the associated physical and logical scope in charge of this implementation, which is important for the evaluation. But then not all root MCUs, MPUs will implement only those core security features. They may implement more to provide more supports to customers building their IoT devices. In this case, the MCU developers also want to extend the security claim and then provide more evaluation evidences reusable by their customers for further composition and compliance demonstration to the IoT standards. So for that, Augmentation packages can be defined in separated document or not, and can be added to the core MCU MPU profile claim, either under the same evaluation or separated. So you could have, for instance, one package per standards, for instance, the 03645, which this package will add all the needed requirements and the conditions to be considered during the evaluation for being reusable for compliance demonstration. So this is it for the security features claim part. But the MCU MPU profile also provides important information for the vulnerability analysis and security testing, as we will see it now. So before going into the MCU MPU specific case, here is just to show briefly the generic security testing process in SESIP evaluations. So a set of developers' inputs is provided to the security lab in charge of the evaluation. Part of those inputs, you may have the source code, depending on the security level claimed, some technical documentations, information also about the developer testing campaign, and of course, samples for the evaluation. So in SESIP, all those inputs are requested as support for the security testing, no matter the format, as long as the evaluator has the needed information useful for testing, this is what is required. Anyway, the test plan then depend, of course, of those information provided, of the implementation analysis and the potential weaknesses found during the analysis. But which tests are applicable or not also mainly depend on the security claim, which one is based on the SESIP profile. So coming back to our MCU MPU profile, it has been developed to take into consideration the different possible environment defined in SESIP. So in the base conditions, which corresponds to the MCU MPU base profile, it is considered that victim device will not be physically accessible by attackers. The typical example is home automation IoT devices, for which it was not really relevant to provide physical protections while the device is in your house and then not really accessible to external attackers. Also, in the base conditions, it is considered that the IoT device do not provide the possibility to load untrusted code. This can depend on cases, but basically a code can be said to be untrusted as long as it has not been verified to be harmless against the MCU MPU, because this is our scope today. So untrusted code can be coming from final users or even also developers integrating the MCU MPU. If the code has not been checked that it could not hurt directly or be used to hurt the core MCU MPU features, it can be considered as untrusted. So in the base context of the profile, there is no such mechanism to load untrusted code. Many IoT device will not need to allow this user code loading, for instance. I guess that things like connected light or fridge will not implement such mechanism, even less sensitive products as control units in industrial appliance, for instance. So under these conditions, only remote attacks against victim devices can be part of the test plan. No local attack, no local physical attacks or local software loaded into the MPU will be considered. So just a word, why victim is underlined. This is because there is a slight precision to add that there are still physical attacks to be taken into consideration by the evaluators during the evaluation, which are the ones that an attacker can do if he owns an instance of the device and With physical manipulations, he's able to build a remote attack against other devices, for instance, by disclosing a master private or secret key. So this specific case is part of the testing scope, even if the physical attacker resistance is not claimed, because this ends up with into a remote attack. So it corresponds to the expected environment. Now, if the IoT device is intended to be used in a public environment, as in offices, for instance, or if the owner of the IoT device can itself be the attacker also, then physical resistance feature need to be implemented and evaluated. In this case, the extra physical attacker resistance package will be selected and be part of the security claim. And then the security testing plan will include physical attacks. Also, if it is known that the IoT device offers the possibility to load untrusted code, that could be used to locally run software attacks. Then isolation protections need to be implemented and evaluated. Then in this case, the software isolation package will be selected and be part of the security claim. And the security test plan will include software attacks that could be run locally. The other aspects impacting the security testing plan is the resistance level part of the SESIP assurance level definition. I will not go here into details of what is an assurance level exactly. The only thing interesting for the security test plan, security assessment, is the resistance aspect. So for information for the ones who knows about common criteria, each SESIP level corresponds to an AVA VAN level. So for the other ones, what needs to be known is that 5 levels of resistance are defined. They are corresponding to a rating that is more or less reflecting the attacker profiles, its expertise and its equipment, but not only. So it's a bit more complex than that. But what can be said is that the MCU MPU profile. In this profile, the different security levels are possible, depending on the security features that have been claimed. So if you remember, the use cases defines the security feature to be claimed, and those security features implementation defines or impact at least the resistance level that can be claimed. And this resistance level itself define the type of attack applicable and that can be part of the security test plan. We will see in the next slide a more concrete example, but just before, see that for the base profile and the crypto extension only, SESIP2 can be claimed, which corresponds to what we can call basic attack potential. Let's consider that as attackers with a low expertise and no specific equipment, nothing expensive at least. So this level can, in the SESIP profile, can only be raised with the claim of an extra attacker profile. So it can be raised up to SESIP 3 with the software isolation claim, which means resistance to what we call enhanced attack potential, so more expertise and more equipment than in the basic one. And it can be raised up to SESIP 5 with the physical attacker resistance claim, meaning a resistance to a high attack potential involving a high level of expertise and equipment very specialized, not publicly accessible, or very, very expensive. So let's see a bit more concretely what does this means in terms of attacks. Just before, this is important to understand that this table is a really simplified analysis. It's not fully following showing the common criteria schemes, but it gives an idea of the applicable tests depending on the core MCU MPU security claim. So you can see that first lines, those very high level advanced physical manipulation requiring very high expertise should only be applicable when physical attacker resistance is claimed along with the SESIP 5 level. So either with the physical within the physical resistance package or within the secure enclave package in which the physical attacker resistance has been selected. Fault injections attacks will also be applicable when physical attacker resistance is claimed, either or not in the secure enclave, but along with SESIP level 3 to 5 this time. Advanced fault injection will be more for SESIP 4 and 5, and basic for basic fault injections, more for SESIP 3. But also, basic fault injections may be applicable if, I would say, very easy with non-expensive equipment and a bit of expertise. It could be applicable to the SESIP level 2 for this specific context I explained before, where the attack is done on the attacker device and lead to a remote attack, and only in this case. Same things for simple physical attacks as glitches or simple memory dump, basic side channel analysis. Advanced side channel analysis should not be applicable to SESIP 2 because it's an attack potential a bit higher. Then you have the basic logical attacks that are applicable, of course, in any case. And you have more advanced logical attacks for which it will depend on the SESIP level. This separation of logical attacks between basic and advanced is really an indication. The examples are really indications. It's absolutely not something that is fixed. And so this will really depend on the rating of each specific attacks. So this last slide is just to represent the details we've just seen about the security claim aspects impacting the security testing plan. So the use cases allow defining the security features or reversely, and the security features allows defining the security levels. Again, it could be reversely. As a conclusion, the core MCU MPU security evaluation is the fundamental step for the security assessment of a full IoT device, as it is the root of security for those devices. So the core MCU MPU SESIP profiles defines those really core security features to be implemented, so to be this root of security. And it also provide essential informations for the determination of the attacker profiles to be considered for the security assessment, security testing plan definition. Then a certificate against this profile aims at supporting the customer to be informed about which security features are implemented, which type of attacks it is resistant again, under which environmental conditions this security is ensured. So how, in which type of devices, and he will be able to sell his IoT device. It also provides the evaluation evidences reusable directly for demonstration of IoT of compliance to IoT standard requirements, at least the requirements are requested to be provided by the core MCUs, and potentially its extensions, as we have seen, um, or it can be reused also in the composition of for different in different products. So at final, it raises the security of IoT devices by making the security assessment of complex devices feasible in terms of cost and efforts, and also helping supporting technically those security assessments. So thank you very much for your attention, and now I'm ready for the questions, if any.
Thank you very much, Eve, for the presentation. We did get two questions. One of them is, does SESIP has dependency on CC? Meaning, is it necessary to achieve CC before going for SESIP?
So for the SESIP levels 1 to 3, it's independent. You don't need to have a CC certification. But for SESIP 4 and 5, this is indeed needed because here we are on higher evaluation levels. So there are other requirements. So for now, SESIP 4 and SESIP 5 requires a CC certificate, not the lowest one. Just maybe to mention that SESIP is based on CC. It has taken from the common criteria I would say the parts that are usable in for IoT devices evaluations. And what has been changed is the security functional requirement, what we have called the security requirements.
All right, thank you. Another question is, also, does CSIP limit to ARM architecture? Does it apply to other architectures such as RISC-V?
Yeah, it's completely independent of any architecture, any implementation. It's really covering any type of devices.
Thank you. And I think there is another question. In the meanwhile, if anyone else has a question, please type them in the chat box. So the next question is, what is the difference between the software isolation functionality in software isolation profile and the software isolation functionality inside secure enclave profile?
Okay, so maybe I use different terms, but software isolation, there is only one set of requirements about software isolation. So there are different type of software isolation between the IoT platform and the application, between the applications to be using the IoT platform, and for parts are in the platform itself. But this is the same software isolation package. And about the secure enclave, so this is the same. The secure enclave is claiming this software isolation requirement. So this is within the secure enclave package. In fact, you have the package under which you have different security requirements. And I think what is maybe a bit confusing is that you have the name of the package, which is the software isolation package, which is inside claiming the software isolation requirements. And you also have the secure enclave package that can claim the software isolation requirements.
All right, thank you. And I think I see one last question. Katalin is asking, where can we read more about this? Are there any MCU MPUs that went through SESIP so we can see some example reports?
So you can find the MCU MPU profile has just been published. Yeah, maybe yesterday or a few days ago. So for now, there is no use example of this package, I guess. But you can have the profile itself on the global platform webpage on this website.
All right. Thank you very much. Are there any more questions? If yes, please send them across in the Zoom chat box. Let's wait a little bit. I believe that's all. So Eve, thank you again for answering the questions and for the presentation. It was a great pleasure having you with us today. This concludes the webinar. Please don't forget to fill in the feedback form. I shared the link in the chat box, and you will also get a pop-up after the webinar is over. And also we have our trainings and conference coming up, hardwear.io USA, between the 5th and the 10th of July. I also shared the link in the chat box, so please go check it out, and we hope to see you there. Thank you all for attending today's webinar, and hope to see you next week as well.